Hello everyone. In this module, we are going to study about three important topics in 1H NMR spectroscopy, that is nuclear over-Auster effect. In short, we call it as NOE. The next topic is variable temperature NMR, and the last is Fourier transform NMR, that is FT-NMR. We will take up one by one in detail now. First, we will see what is nuclear over-Auster effect. It is NOE, abbreviation is NOE. Say for example, you have a molecule. In that molecule, if you want to see if the two protons are nearby each other or not, then you have to go for nuclear over-Auster effect. Here, over-Auster is the name of the scientist who discovered this effect, and in the honor of him, they have named this effect as nuclear over-Auster effect. This nuclear over-Auster effect is mainly dealing with the property of the molecule in which if the two protons are nearby each other, then it will be easily identified by NOE. This effect was first discovered by Overhauser in the year 1953. The main application of NOE is to see whether the two protons or the group of protons are present in close proximity or not within the molecule. Along with that, there is one more application, that is, you can find out which geometry the molecule is possessing, whether it is present in E or Z form or cis or trans form. So what happens in this technique or in this effect is you can enhance the signals by double irradiation. The double irradiation, whatever you have studied in the simplification of complex spectra, the same double irradiation technique here we are going to use. Say for example, there are two groups of protons. For one group of proton, I do double irradiation. Once I do double irradiation, the signal of the other proton will be enhanced. Whenever there is this enhancement in the signal, we can say that the two protons are nearby each other. Whatever may be the number of intervening bonds between the two groups of protons, it is immaterial here. Let us see by taking the example of this molecule. Consider a molecule of this type wherein there are two protons, HA and HB. So let there be any number of intervening bonds. That means the bonds between HA and HB is immaterial for us. But the main priority or criteria here is the distance between the two protons should not be less than 3.5 angstroms. If it is more than 3.5 angstroms, then NOE effect will not be observed. Say for example, here there are two types of protons, HA and HB. Now what I do is, I want to see whether these two protons are staying nearby each other or not. For that, what I will do, I will keep HA constant, I will double irradiate HB. When I do double irradiation for HB, that means I'm giving more radio frequency energy. Because of more radio frequency energy, here the stimulation is passed through the relaxation mechanism. The stimulation is passed through the space to the relaxation mechanism of HA. So whenever the stimulation is passed from one proton to other proton, the intensity signal of this proton will be enhanced like anything. Whenever the enhancement is taking place of this particular proton, you can say that HA and HB are close to each other or they are in close proximity. Or I can do in this way also. I'll keep HB constant, I will double irradiate HA. Because of extra energy, it will stimulate, this proton gets stimulated and the stimulation is passed through the space to the relaxation mechanism of HB. Now, the intensity of the signal of HB is greatly enhanced. Now I can say that HA and HB are close to each other. The enhancement of the signal is by nearly 15 to 50%. Because the signal of HA is enhanced, I can say that HA and HB are in close proximity with each other. As I said earlier, HA and HB, they should not be separated by more than 3.5 angstroms. That means the distance should be within 3.5 angstroms. If it is greater than 3.5 angstroms, then you will not see NOE. And one more care should be taken while performing NOE, that is, you should carry out on deoxygenated sample, because the molecular oxygen present in the atmosphere, it can contribute to the nuclear space lattice relaxation processes. So whatever NOE you conduct, it should be in a deoxygenated sample. Let us look at some of the examples in order to understand better this NOE. So this is isovanillin. In this isovanillin, I will consider these two protons, methoxy and HX. I want to see whether these two protons are in close proximity with each other or not. So what I do, I will double irradiate this methoxy group. When I double irradiate this methoxy group, the signal of the HX will be enhanced like anything. Now I can say that OCH3, that is methoxy, and HX are close to each other, and that type of interaction is known as NOE interaction. So this is the first application of NOE. The second application of NOE is that we can predict the geometry of the molecule. Say for example, this is a derivative of ethene. Here there are two methyl groups, one carboxylic acid and one proton. Now imagine I will label this CH3 as A, I will label this CH3 as B. What I do now is I will double irradiate this CH3. When I double irradiate this CH3, the intensity signal of Hc is dramatically increased. Now I can say that CH3 and H are in close proximity. That means they are present in the same part, and hence I can say that it is cis-methyl. Whereas if I double irradiate this CH3A, then there will be no signal enhancement of Hc. Now I can say that CH3 and H are trans to each other. This is how you can easily assign cis and trans or E and Z configuration to the particular molecule by making use of NOE. Other concept that you have to understand here is NOE difference spectra. You can clearly see here how the signal enhancement will be taking place. Consider a molecule of this type. This is anthraquinone. In this anthraquinone, now there are many aromatic protons. I want to see which protons are nearby each other and where NOE interaction can be seen. For that reason, what I do is I will double irradiate this proton at carbon 5. When I double irradiate at proton carbon 5, the intensity signal of the proton 10 is increased dramatically. See here, this is without double irradiation and this is after double irradiation. This is proton number 10. See here, proton 10, and see here also proton 10. This is after NOE. You can see that here the intensity of this particular peak is very, very less, whereas the intensity of this particular signal after NOE, it is greatly enhanced. It is roughly by 30 times greater percentage of the enhancement. And hence I can say that these two protons are close by each other. You can see that this is a three-step transfer mechanism. First, the mechanism is the stimulation is passed from proton 5 to proton 6. Proton 6 will transfer the stimulation to proton 9. This proton 9 will stimulate the transfer to the proton 10, and hence I can say that. And also these two 5 and 10 protons are exo to each other. Exo means outside the ring, and hence there will be a great enhancement of the proton at 10. Now I can say that proton 5 and proton 10 are close to each other. That means it should be within 3.5 angstrom. This is the NOE difference spectra. NOE difference spectra is nothing but first you carry out the NMR without double irradiation. Next you carry out after double irradiation. Then subtract the later from the former. You will see that wherever there is a enhancement in the signal, only such signals will be shown in the NOE difference spectra. So this is the NOE difference spectra of anthraquinone. Next, we will go for another important topic in 1H NMR spectroscopy or C13 NMR spectroscopy, that is variable temperature NMR. So as the name itself is telling, variable means we are changing. So constant, opposite of constant is variable. Constant is the one which does not change. Variable is the one which keeps on changing. So it is variable temperature NMR. That means whenever you want to run an NMR, you can change the temperature. So usually two types of variations in temperature we can do. One is increasing the temperature, another one is decreasing the temperature, or you can say high temperature and low temperature. How you can do high temperature? It is obtained by passing a gas of air or nitrogen through a heater. So you will have a sample tube, keep that sample tube in the NMR spectrometer, and then pass the gas of air or nitrogen through a heater. So the sample gets heated. What is the effect? What is the result of heating? We will see later. Or the cooling you can do by using a coolant. Usually it is liquid nitrogen, or you can utilize Joule-Thomson effect. So Joule-Thomson effect speaks about cooling down the temperature. So these are the mainly two temperatures at which we can record NMR. So at high temperature or at low temperature. Usually the NMRs are done in room temperature. If the peaks are not clearly seen, you can go for either high temperature or low temperature NMR, and hence such a type of NMR is known as variable temperature NMR. So what is the application of this variable temperature NMR that we have to see now one by one. It is possible to study the restricted rotation or ring inversion in the molecule by the application of variable temperature NMR. Now you want to see whether the molecule can rotate, or a particular atom or group of atoms can rotate within the molecule or not. And also you can see whether there is any ring inversion in the molecule. This is mainly applicable for ring molecules. If the ring molecules, there you know that there will be flipping in the molecules in the ring system. If the flipping has taken place or not, that you can easily study by making use of variable temperature NMR. So as the first example, we have taken the NMR of DMF. DMF is dimethyl formamide. To be more precise, we call it as NN dimethyl formamide. What happens is, when you record the NMR of this DMF at room temperature, it will show two signals for the methyl groups. This is the structure of DMF, N-dimethyl formamide. So there are two types of methyl groups. When you record the NMR of this DMF at room temperature, you will see that there will be two different peaks for two different protons. You consider this as proton methyl A, and this is methyl B. Methyl A will give a singlet, methyl B will give a singlet. So at room temperature, there will not be sufficient energy for the molecule. Because of that, there will be very, very slow rotation at room temperature. When the molecule is rotating slowly, this CH3 will distinguish itself from the other CH3 group, and hence both will appear as different. It is because of that reason you can see that there are two different peaks for two different methyl groups at room temperature. Also, another characteristic feature that is involved in DMF is there will be shifting of the double bond. Here, the lone pair of electrons on the nitrogen, it will come here, and the negative charge is given on the oxygen. So there will be resonance, and you can see that there will be partial double bond character. So in principle, when you record the NMR of the DMF at room temperature, you will see three peaks, one for methyl A at 2.8 ppm, one for methyl B at 2.97 ppm, and another for the aldehydic proton around 8.02 ppm. So when you increase the temperature from room temperature to 130 degrees centigrade, because of the fast rotation, so whenever you are increasing the temperature, you are providing more energy. When you provide the more energy, there will be more activation in the molecule. More the activation, more the rotation. There will be more rotation about this CN bond. Because of the fast rotation, this two methyl groups will appear as one. Both will resonate at a single frequency. So instead of getting two peaks, you are going to get only one peak at 130 degree centigrade. So at 130 degree centigrade, there will be fast rotation. As a result of that, two methyl groups are recorded as one. So at room temperature, you will have two peaks for two methyl groups, whereas at elevated temperatures or high temperature, you will see that both the methyl groups will appear as only single peak. This is how you can study the variable temperature NMR. Another example we will take, the ring inversion. So by saying, you know that this is cyclohexane. In cyclohexane, this is the chair form. You know that in cyclohexane there are two types of protons. One is axial, another one is equatorial. So at room temperature, what happens is, because at room temperature, the molecule will be shifting from one form to another form. This is called ring flipping. So by calculating the energy of activation, you can say that whether the molecule has undergone ring flipping or not. So it is possible to calculate the energy of activation for the rotations by noting the temperature at which the rotational or inversional interconversions begin to occur. So here you have cyclohexane. This is axial proton and this is equatorial proton. When you calculate the energy of activation, it will give some X value. So after some time, if you see that the molecule will have undergone inversion or ring flipping has taken place, wherein the axial and equatorial proton will change its position. As a result of that, energy activation is also changed. So you can say that here you have got energy of activation X, Here you have energy of activation Y. So if you get both the energy of activation, we can clearly say that the cyclohexane at room temperature will involve ring flipping or inversional interconversions. This is another application of variable temperature NMR. We will take third example. This is the case of N-methyl 2,4,6 trinitroaniline. Here there are two aromatic protons. These two aromatic protons, when you do the NMR spectrum of this at room temperature, both will appear as only a singlet. This is at room temperature. So the last case with DMF was at high temperature. Now we will see what happens when we carry out the NMR at low temperature. So the same molecule, when you do the NMR spectrum at low temperature, say minus 60.7 degrees centigrade, you will see that these two protons, it will distinguish itself from one another, and hence this will think that this is different proton, this will think that this is proton, because of the very slow rotation of this N-methyl group. At room temperature, there will be fast rotation. Because of the fast rotation, these protons will think that they both are one and the same. Whereas at low temperature, as the temperature goes down, the energy also comes down. When the energy comes down, there will be very slow rotation of this N-methyl group. So this N-methyl group is at the midpoint of these two protons. Because of that slow rotation, this proton, it will think that, okay, this is different proton, and this will think that this is different proton. So this will think that this has the neighbor 1 plus 1, 2. This will think this has the neighbor 1 plus 1, 2. So this will also give a doublet, and this will also give a doublet here. And that is clearly shown in this. This is the only aromatic region. Aromatic region only of the 1H NMR spectrum of N-methyl 2,4,6 trinitroaniline. So here at room temperature, it will show only one peak, whereas at low temperature, it is showing two peaks for two different proton, and each peak is split into two. So you are going to get doublet of doublet at low temperature. This is another case of 1,3,5-trioxane. This is a derivative of cyclohexane. So when you carry out the 1H NMR of 1,3,5-trioxane at room temperature, both axial and equatorial protons, they appears to be same, because this is a symmetrical molecule, and hence you are going to get only one peak in the 1H NMR spectrum. The same molecule, when you subject it to minus 80 degrees centigrade for NMR spectroscopy, there will be a slow exchange of the equilibrium as shown here. So the ring flipping has taken place here. Because of the ring flipping, axial will show one type of peak and equatorial show another type of peak. So in 1H NMR spectrum of this trioxane at minus 80 degrees centigrade, you will see that there are two kinds of peaks, whereas trioxane at room temperature will show only one peak. So you are going to get two peaks. It is because of the reason that axial and equatorial protons are identified as different, whereas at room temperature, they both are identified as one and the same. And hence here you are going to get only single peak. Here you are going to get two peaks, one for axial, another one for equatorial. Now we will take up the next topic, that is Fourier transform nuclear magnetic resonance spectroscopy. In short, we call it as FT-NMR. We have seen earlier about the instrumentation of NMR and in what way this FT-NMR is different. That is what you have to understand first. In NMR, you will see that you will have a sample. That is, sample is put in the NMR tube, and you will place that sample tube in between the magnets, and you will supply the radio frequency energy. So in normal NMR, what we do is either we keep the radio frequency energy constant and we vary the magnetic field, or you keep the magnetic field constant and you vary the radio frequency energy. And you will see that the sample will absorb the required energy, and it will go to transition from lower state to higher state. The molecule which has gone to higher state, it will not stay there itself. It will definitely come back to the original state by means of relaxation processes. So this is what is happening in normal NMR, and that we call it as continuous wave NMR. Whereas this Fourier transform NMR, it involves that you will have a constant magnetic field and a constant radio frequency. So the radio frequency that you put for the instrument will be of the higher order. So in this method, what we normally do is we excite all the protons at a time rather than one by one. Whereas in the normal continuous wave, that is CW NMR, we successively excite the proton one by one. Whereas in FT-NMR, we excite all the protons simultaneously rather than successively. As I said earlier, in CWNMR, we keep magnetic field constant and radio frequency is varied, or radio frequency is kept constant and magnetic field is changed. Whereas in FT-NMR, you won't see that type. You will see that the sample is irradiated at a fixed field with a strong pulse of radio frequency energy. When that is done, you are supplying more energy to the molecule at a constant speed. So what happens? The protons present in every type of environment, it will absorb a suitable frequency from the radio frequency transmitter, and they will form pulse, and these frequencies couple to give what is known as beats. So when the molecules absorb the required energy or required frequency at particular wavelength, and they couple to give what is known as beats. So following each pulse, you will see that the nuclei are continuing to emit the signals at their characteristic frequency when they come back to the ground state. So this is the characteristic feature of Fourier transform NMR. You are exciting all the protons together at a constant speed of radio frequency energy, and they all will be coming back by emitting energy at their own characteristic frequency. This emission followed by the excitation pulse is known as free induction decay. In short, we call it as FID. So this is how FT-NMR is different from the CW-NMR or conventional NMR. This FT-NMR, it has come into existence during 1970s, and this FT-NMR, it has got high advancement in recent years, and you will see that in most of the companies or most of the research institutes, we are going to use FT-NMR, and this conventional NMR is rarely used nowadays. This is the block diagram of FT-NMR. So you will see that you have the sample tube in which you have placed the sample, and you have kept the sample tube in between the external magnetic field or the magnets. So this is the frequency synthesizer, wherein the appropriate frequency required for the excitation of the different protons are synthesized here, and this will go to the pulse switch. From the pulse switch, it will be transmitted through a radio frequency transmitter to the sample. Now the sample will absorb the appropriate frequencies. So once the sample is absorbing the frequency, it will create beats, and that is called free induction decay. Once that all the protons have come back to the normal ground state by process of relaxation mechanism, all the samples will be amplified in the radio frequency amplifier, and that will go to the detector. So once it comes to the detector, it will go to the computer. So the main difference between conventional NMR and FT-NMR is that when you do normal NMR, you will get the simple spectrum, because each proton is excited successively but not collectively. Whereas in FT-NMR, you are exciting all the protons together, which results in the complication of a spectra. You are going to get a very, very complicated spectra. If you just look at the spectra without any transformation, you will see that all the peaks are buried inside. They all appear as multiplet. Thanks to the nature, thanks to scientists, we have got Fourier transform mathematics. By using Fourier transform mathematics, it is the formula. So the system itself will convert the complex spectra into simple spectra, and that will be given in the output as video or hard copy. So this is the block diagram of FT-NMR spectrometer. So here the pulse duration will be of very, very short duration. It's approximately 10 microseconds. And when the frequency, external frequency which is given is switched off, the nuclei undergo relaxation process and re-emit the absorbed energy and coupling energies. So all the re-emitted energies are simultaneously emitted. As a result of that, a complex interacting pattern is obtained. This pattern is digitized in a computer, and each individual frequency is identified from the interfere patterns by means of mathematics of Fourier transform. So then we plot the frequency on a linear frequency scale, and that is called the NMR spectrum that will be obtained on the output of the instrument, that is computer. Then we have to know the advantages that are associated with FT-NMR. You will see that an entire spectrum can be recorded in few seconds, but in conventional NMR it will take minutes to hours, whereas in FT-NMR in few seconds you will see that the whole proton NMR or see that NMR is recorded here. Nearly in 30 minutes, you will see that 400 spectra can be recorded, and along with that, you will see that 20 times the signal enhancement will be taking place if you use FT-NMR. So other important application or advantage of this FT-NMR is that even if the sample concentration is very, very low in the sample test tube, then it is able to detect the number of peaks present in the molecule. That means you can easily arrive at the structure of the molecule even if the sample concentration is very, very small. And also there are many isotopes. You will know that all the isotopes of a particular element will not show NMR whose spin quantum number is greater than half, that is I greater than 0, it will show NMR. So if the molecule has got very, very low natural abundance, even such nuclei can also be subjected to FT-NMR. The last advantage is that even if the nuclei has got very, very small magnetic moment, then that can be subjected to FT-NMR. So these three advantages has made FT-NMR to boom in the 21st